Hi everybody, I am Dr. M. Muruganandam. I am working as an associate professor in the Department of Mechanical Engineering in PSN College of Engineering and Technology, Melathiriyu, Tirunelveli, Tamil Nadu, India. I am going to give a lecture, 1 hour lecture on mechanical vibrations, where I am going to discuss about transfer matrix methods and critical speeds in lateral vibrations or bending vibrations. In the day-to-day industrial operations, in the design and maintenance of machinery, it is very important to know about the lateral vibrations or bending vibrations. The machinery are subjected to lateral vibrations, bending vibrations, such as turbines, compressors, pumps, power transmission systems, which are under bending vibrations or lateral vibrations. During the manufacture of the rotor, the balancing is done. During the assembly of the rotor, the balancing, whatever the degree to which the balancing is done, some residual unbalance is present in the rotor of turbines, pumps, compressors and power transmission systems. The unbalance in the rotor leads to vibrations. The knowledge of bending vibrations or lateral vibrations is very important based on the day-to-day problems that occur in industries, mechanical industries. There are various methods by which the vibrations, bending vibrations, lateral vibrations can be analyzed, such as Dunkerley's method, Rayleigh method, transfer matrix method, finite element method. The increasing speed of computation using computers leads to increased use of finite element methods in vibration analysis. Dunkerley's method and Rayleigh method are based on the techniques where only the fundamental critical speed or frequency of vibration is found, whereas in a real rotor, where we have a large number of discs are present, apart from the fundamental frequency of vibration, there are other frequencies of vibration which are falling outside this fundamental frequency range over the entire range of operating speed of the rotor. A maintenance engineer or a design engineer is forced to use methods other than Dunkerley's method and Rayleigh's method. So transfer matrix method is one of the methods by which the frequencies, critical speeds over the entire range of operational speed of the rotor can be found. What is the critical speed of rotation of a rotor? Let us take this schematic representation of a rotor where it consists of a shaft and a disc. The disc is having a mass m and the rotor is moving with the speed of omega radian per second. The unbalance in the rotor, due to the unbalance in the rotor, the mass center of the rotor G is at an eccentric distance E from the shaft center S. The mass center of the rotor G is at a distance of E from the shaft center S. When the rotor is at motion, there is an exciting force equal to m omega square W, which is the bending deflection of the rotor, is acting on the rotor when the mass center of the rotor coincide with shaft center. Even in a balanced rotor, we have such a condition of exciting force. It's a varying force. When the shaft is rotating, it varies in direction. Due to this force, the rotor is under bending deflection, bending vibrations. The rotor is at bending vibrations. The objective of this presentation is to find out the frequency of that vibration corresponding to the natural, when this vibrational frequency equals the natural frequency of the beam under bending, the speed of rotation is called critical speed. At that speed, the amplitude of vibrations becomes maximum and it even exceeds the bearing clearance. Thereby, there is a possibility of destruction of the entire rotor bearing system. In order to avoid such conditions of destructive nature of this vibration, it is important to analyze the critical speed of the rotating shaft. So it is the speed, the critical speed is the speed of rotation of the shaft, which coincides with the natural frequency of the stationary shaft in lateral vibrations. In the past, Michaelstadt-Pröll method was used to analyze these lateral vibrations or bending critical speed. Then transfer method matrix form of the above said method, which have been developed by Pestel and Lecky, was being used. Now with the increasing in computing power, finite element method is being used in lateral vibration analysis. The objective of this presentation is to determine the natural frequency of a stationary shaft which is undergoing lateral vibrations using transfer matrix method. It is a typical rotor which has two locations in which bearings are present, and there are two discs, turbine 1 and turbine 2. For such a kind of rotor, we can analyze the critical speed in this using this method. This method is based on discretization of the elements. In a real rotor, the mass of the rotor can be discretized into infinite number of elements in a real rotor. In that sense, a real rotor has an infinite degrees of freedom of motion. Whereas in analyzing such a real rotor with such an infinite number of degrees of freedom, the mathematics involved, the equations involved are very tedious, that we go for finite number of masses in a real rotor. The mass of a real rotor is discretized into finite number of elements. Here the entire rotor is discretized into n number of elements, n mass system. Each and every mass is assumed to concentrate in a location called disk. A disk is a turbine wheel, a ring of blades in a turbine, or a ring of impellers in a pump or a compressor, or it may be, in the case of a power transmission system, there are a number of gears. Each gear can be taken as a disk. In between the disks, the portion of the shaft is taken as an elastic member. So here in this method, transfer matrix method, the entire rotor, which consists of disks, shaft and bearings, are discretized into n number of elements or n number of masses. Each mass corresponds to a disk location. In between the masses, point masses, which are called point masses, the portion of the shaft is considered as an elastic member, where we have n number of elastic members. The properties, the stiffness properties of the members are used to define the elastic members. The inertia properties of the disks are used to define the point mass members. And these are the locations where the bearings are located. Bearings are present. The red color one. It may be a rolling element bearing or a fluid filled bearing. The masses are lumped with their gyroscopic inertia neglected. In an ith element of mass, there are states represented by S, the state of a node. The mass, each mass is called a node. The state of each node is defined by the following vectors. It shows the coordinate system for the rotor, x-axis along the length of the rotor, and y-z plane is perpendicular to the axis of the rotor. Z is along the vertical direction, y is along the horizontal direction. So these are the vectors which define the state of a point node. What are the vectors? V is the shear force, M is the bending moment, theta is the slope of the rotor, and W is the deflection of the rotor. Using these four quantities, the state of a node is defined. The state of an ith node is given by Si. Since it is to the left side of the ith node, it is represented by a superscript L. The state of ith node to the right side of that node is represented by the superscript R. The state of the I minus 1th node is given on M minus 1. The state of the I plus 1th node is given on the point mass Mi plus 1. The distance between the I minus 1th node and ith node is given by Li, which gives the length of the elastic member between the two nodes. The equilibrium relations are used for arriving at the equations, governing equations for shear force and bending moment. The Newton's laws of motion, Newton's second law of motion is applied on the elements, point masses and elastic elements to arrive at the relations between the shear forces to the left and right side of each node, the bending moments to the left and right side of each member, elastic member. Newton's second law of motion is used on these elements. Here the deflection curve of a typical beam is shown, where the deflection at the one end is 0, deflection at any other point is given by W. The slope of the deflection curve at a point is given by theta. The bending moment at that point is M, which is directed towards the y-axis. The shear force at that point is V, which is directed towards z-axis. An element which is in between the I minus 1 and ith node is shown here. The flexural rigidity of this element is E into I, where E is Young's modulus and I is mass moment of inertia of this shaft. So moment of inertia of this shaft cross section. The deflection of the element node I minus 1 to the right side of the I minus 1 element and deflection of the element to the left side of ith node are shown here, along with the corresponding slope theta L, theta R, bending moment L, bending moment R, shear force R, shear force L are shown here. The directions are shown here. Using this Newton's second law of motion, the relations between the shear force acting on this element VIL, VI minus 1 R are arrived. The relation between the bending moment to the right side of the I minus 1th element to the left side of the ith element are shown here. These two bending moments are acting on this element I of the beam. The bending moment diagram is shown here with respect to the length of the beam X. Using this relation, we can arrive at a general relation between the bending moment at any point along the axis of the rotor using the bending moment of the I minus 1th element and shear force of the ith element using this equation. The slope of the element d theta is given by this equation, where R is the radius of curvature of the deflection curve. S is measured along the deflection curve. ds is the element of the deflection curve, elemental length of the deflection curve. My is the bending moment at that cross section. E is the Young's modulus of the material of the beam. I is the area moment of inertia of this beam. about y-axis. Using Euler-Bernoulli beam model under pure bending, this equation is arrived. The stresses in a rotor which is subjected to later loading is defined by the shear force acting at the cross section of the rotor and bending moment acting on the cross section of the rotor. When the bending stresses alone are used or considered or significant, then we say that the rotor is under pure bending conditions. Under pure bending conditions, any two adjacent cross sections of beam M and N at a distance dx apart will intersect after a bending at an angle d theta, which is given by this Euler-Bernoulli beam model. Neglecting curvature as applicable for beams and structures, the elemental distance ds can be equated to or made equal to the distance dx along the axis of the rotor. Integrating this equation over the ith portion of the beam, we can obtain the relation between the slope of the deflection curve of the ith element to the left side of the element in terms of the bending moments and flexural rigidity, which is the product of Young's modulus and area moment of inertia of the beam cross section. This equation is based on area moment theorem 1. And as per this, graphically this equation says that the change in the slope along an element of length Li or dx, element of length dx, is equal to the area of the bending moment diagram, area under the bending moment diagram. My is the ordinate of the bending moment diagram, dx is the abscissa of the bending moment diagram. The area of this rectangle my into dx divided by the flexural rigidity of the beam which is under consideration. This is called first theorem of area bending moment diagram. Area bending moment first theorem. Using this area of the bending moment diagram first theorem, the slope of the change in slope of the deflection curve is obtained. Integrating this equation of deflection, elemental deflection, will lead to change in slope over a given element of ith element. The distance of the vertical distance along the z axis from I minus 1 can be represented by I dash which can be found by the moment of this area inside the bending moment diagram, that is area is m into dx, m is bending moment, dx is length of that element in the bending moment diagram. So m into dx is the area of this bending moment diagram, ei is the flexural rigidity. The moment of this area under the bending moment diagram is given by x dash into m dx. X dash is measured from the point of I towards the elemental area inside the bending moment diagram. So the first moment of this area under the bending moment diagram divided by flexural rigidity will be equal to x dash d theta, which is nothing but the vertical distance along the z axis of I dash, which is equal to the change in the deflection from I minus 1 to I. Our vertical distance of I with respect to I minus 1 is given by this equation. By integrating this equation, we can obtain the vertical distance from I to I minus 1, which is nothing but the change in deflection, WIL minus WI minus 1 R, where x dash is equal to Li minus x, where x is measured from I minus 1th node, x dash is measured from ith node. So Li is the length of this element, ith element. So x dash is equal to Li minus x, theta I minus 1 is 0, using which we can find the WIL, which is the deflection of the ith element. Wi minus 1 is deflection of the I minus 1th element. Superscript L indicates it is the deflection to the left side of the ith element. Superscript R indicates it is the deflection to the right side of I minus 1th element. Can be found using the shear force, bending moment, slope and other constants, which are length of the element, flexural rigidity of the shaft rotor. We have 4 equations. The equations for bending moment and shear force are arrived by applying the Newton's second law of motion. The equations for deflection and slope are arrived by applying the area moment theorem 1 and area moment theorem 2. Whereas area moment theorem 1 is given by this equation, where graphically the change in the slope is equal to area of this bending moment diagram divided by flexural rigidity, that is area moment theorem 1. Here change in the deflection x dash d theta, or the vertical distance from I and I minus 1, is given by the first moment of this area under the bending moment diagram divided by flexural rigidity, which is called second theorem, area bending moment second theorem. Using the area bending moment first theorem, the equation for slope is obtained. Using the area bending moment theorem 2, equation for the deflection is obtained. These 4 equations, algebraic equations, can be rewritten in the form of matrices, where the matrix of vectors of the ith element is related to the matrix of vectors of I minus 1th element. That is, the state L to the left side of ith element is related to the state of the node to the right side of I minus 1th element, using the coefficient matrix, which consists of constants such as length of the element, flexural rigidity of the rotor. So in abbreviated form, the state vector, ith state vector to the left side of the ith vector is related to the state vector I minus 1 to the right side of I minus 1, using the field matrix Fi. The field matrix is a matrix of coefficients which are defined by the elastic properties. stiffness properties of the materials such as L, E and I. Similarly, the equations can be arrived for a point mass. Till now we have seen the matrices for field element, which is the element between two point masses. For the point mass, we can arrive at the matrices which is called point matrix using the equilibrium relations for ith point location of a beam, where the shear force is acting vertically downwards, bending moment is acting anti-clockwise. These are the positive directions for the shear force and bending moment. Using the Newton's second law of motion, the equations for shear force and bending moment are arrived. Using the area moment theorem 1, the relations for theta is arrived. Using the area moment theorem 2, the equations for deflection W is arrived. Thereby, we can relate the state vector of the ith point mass to the right of the ith point mass with the state vector to the left of ith point mass using a matrix called point matrix, which consists of only inertial properties of the rotor, such as mass of the rotor and P, which is called natural frequency of rotation of the shaft or natural frequency of bending of a stationary beam. Now this transfer matrix method is going to be applied for a typical rotor called Kikuchi's rotor, which is shown below. The shaft is made of steel with an Young's modulus of 2.0682 into 10 to the power 11 Newton per meter square. The total mass of the rotor including the shaft is 51.8 kilogram. The shaft mass is lumped at the disc location 2. The point 1 is the location, that is the overhang left end of the shaft. 3 is the overhang right end of the shaft. 2 is the disc location. Point A and B are the locations of bearings. At the locations of bearings, there are reactions PA and PB acting upwards. At the point of location 2, there is a vertical downward force which is equal to the weight of the rotor acting 508.2 Newton, which is corresponding to 51.8 kilogram of the rotor, mass of the rotor. The distance between the nodes 1 and A to 2, 2 to B, B to 3 are given here: 131 mm, 400 mm, 400 mm, 131 mm. Using this data, now we are at a position to find out the critical speed of this rotor or natural frequency of vibration of this beam under pure bending conditions. The state vector at the 0th node is equal to the state vector to the left of the first node, where it is taken that the bending moment is 0 since it is a free end, overhang end. Shear force is also 0. These are the boundary conditions which we apply for the state vector at the location 1. Using this state vector at the location 1 to the left side of the location 1, the state vector to the right side of the location 1, node 1, is arrived using the point matrix 1. Since there is no change in the deflection and slope, we obtain the same state vector to the right side of the node 1. Using the state vector to the right side of node 1, the state vector to the left side of node A is obtained using the field matrix F1A, where L is length of the field from 1 to A, EIY is the flexural rigidity of the beam. Using the equations of motion, Newton's laws of motion and area moment theorem 1 and 2, the equations for deflection, equations for slope, equation for bending moment, equation for shear force are written. Here it is given here that the deflection at the point A, which is the location of the rigid bearing, it is a rigid bearing wherein deflection is 0, both at A and B deflection is 0. This condition is implemented here. Using that, we can arrive at the slope of the rotor, bending moment of the rotor, shear force in the cross section of the rotor at the location A to the left side of location A. Using the condition of W0, the theta 0, that is slope at the location 0 is obtained, which is equal to theta AL. Using that, we obtain the relation between theta AL and W0 and moment AL and W0, shear force AL and W0. At bearing location A, deflection is 0 due to the rigid bearing, slope and bending moment are continuous and there is a change in the shear force. See here, the change in the shear force is represented by PA. PA is the reaction force of the bearing end A, using which the state vector of the node A to the right side of A is obtained. Again, using the conditions of the free end, left end deflection W0 and PA, we obtain a matrix B Now again at the disk location, using the field matrix from A to 2, the state vector to the left of the node 2, which is the disk location, is obtained in terms of the state vector of node A to the right side of node A. Further modifications leads to the relation between the state vector to the left of node 2 in terms of B prime and S prime matrices. S prime is shown here. B prime is equal to B into A prime, where B matrix is shown here, A prime node matrix is shown here. So this method involves successive multiplication of matrices, where the matrices are field matrices obtained from the stiffness properties of the elements in between the lumped masses and the point matrices, which are defined using the inertial properties of the point masses. These matrices are successively multiplied. Multiplying A prime and S prime, we obtain S equation. Successively multiplying B and A prime, we obtain B prime, like that. So the state vector of each and every node is obtained by multiplying the field matrices with the state vector of the immediately previous node. For example, the state vector of node 2 is obtained by multiplying the field matrix with the state vector of the previous node A. The state vector of A is obtained by multiplying the field matrix of the element 1 to A with the state vector of the first node, that is the previous node. As you can see here, the state vector of node A is obtained by multiplying the field matrix in between these nodes 1 and A with the state vector of node 1. The state vector of 2 is obtained by multiplying the field matrix of the element A2 with the state vector of A. Similarly, by multiplying the field matrix of 2B with the state vector of 2, the state vector of B can be obtained by multiplying the field matrix of element B3 with the state vector of B. The element 3 is obtained. State vector at 3 is obtained. So thus the state vector of each and every successive node is obtained by multiplying the field matrices of that element with the state vector of the immediately previous node. By continuing in this way, at the bearing location B, deflection is 0 again due to the rigid bearing conditions, and the slope and bending moment are continuous. There is a change in the shear force due to the reaction force B, thereby there is a change in the shear force VZB with respect to VZB of left side of the node B. Using the conditions of the deflection of the node B is 0, there is a continuous distribution of slope is continuous, theta B R is equal to theta B L, bending moment is continuous, MYB R is equal to MYB L. We obtain the equations of E dash U and E double dash. Finally, we obtain the state vector of 3 to the left side of 3 with respect to the state vector of B to the right side of B using the matrix G, where G is obtained from the field matrix B to 3. In this way, we obtain the final 4 equations which define the state vectors of node 3 in terms of deflection at node 3, slope at node 3, bending moment at node 3 and shear force at node 3. Here the boundary conditions are such that bending moment and shear force are 0 due to the free end conditions. At the point 3, bending moment is 0, shear force is 0. At the point 1 is also bending moment is 0, shear force is 0. At point A in the bearing location, deflection is 0. Bending moment, slope are continuous. At the point B also, deflection is 0. Bending moment, slope, shear force are continuous. There is a change in the shear force. Here there is a change in shear force at A also due to the action of PA. Here there is a change in the shear force due to the action of PB. But bending moment and slope are continuous. At point 3, bending moment is 0, slope is 0. shear force is 0. These conditions are used here. Bending moment is 0, shear force is 0. These conditions are used. We arrive at E double prime equation, which leads to this equation in terms of T31, T34, T35, T41, T44, T45, E11 prime, E14 prime, etc. Where W0 is the deflection at the node 0, that is point node 1, and it is the reaction force at bearing A, it is the reaction force at bearing B. We obtain a system of linear and algebraic equations. Again, these equations are homogeneous equations. Right hand side is 0. For the conditions that the W0 should not be equal to 0, PA should not be equal to 0, PB should not be equal to 0, only then the given physical situation phenomena is validated. For the given physical phenomena where the beam is under bending conditions, lateral bending conditions, these should not be equal to 0. If they should not be equal to 0, the determinant of this matrix given by G should be equal to 0. Using this condition, we can arrive at a function of f of p is equal to 0, where p is the natural frequency of the beam under pure bending conditions. P is natural frequency of beam under pure bending conditions. By solving this equation, that is the determinant of this matrix is equal to 0, we arrive at an algebraic equation in terms of P, which can be solved for P. Thereby, the natural frequency of the stationary shaft in lateral vibrations can be found, which is equal to the critical speed of rotation of the shaft. Thank you, one and all.